Hello, this is a recording of the problem solving session that we did in class on Coulomb's law. Again, you can download the sheet that has these individual problems off of the course e-learning site, but I'm going to walk through my solutions to these same problems in case you got stuck when you were solving the same. So question 1 reads that three identical conducting spheres initially have the following charges. Sphere A has 4Q, sphere B has minus 6Q, and sphere C has 0. A and B are fixed in place and they have a center-to-center separation much larger than the spheres, and two experiments are conducted. In experiment 1, sphere C is touched to sphere A, and then separately to sphere B, and then it is removed. In experiment 2, starting with the same initial states, the procedure is reversed. Sphere C is touched to sphere B, and then separately to sphere A, and then it is removed. What is the ratio of the electrostatic force between A and B at the end of experiment 2 to that at the end of experiment 1? Well, lots of stuff there. Let's go ahead and dive into it. So I'm just going to draw some little pictures. Here's experiment 1. So when I started, sphere C had nothing on it. Sphere A had 4Q, and sphere B had minus 6Q. So after step 1, C touches A, and because they are conducting spheres, then the total charge between the two of them, which is 4Q, is going to be equally distributed among the two of them. So afterwards I'll have C here with 2Q, A also with 2Q, and B still with minus 6Q. Then the second action is to touch C to B and then separate them. So when I put those together, my total charge of 2Q and minus 6Q is a total of minus 4Q, and that again equally distributes among spheres C and B, meaning sphere C ends up with minus 2Q, sphere A ends up with 2Q, I didn't touch that in this part of the experiment, and sphere B is at minus 2Q. Well, let's contrast what happens in experiment 2 then. Again, we start with 0, 4Q, and minus 6Q. After the first action, which C touches B, the total is minus 6 between the two of them. So that means C ends up with minus 3Q. A still has its 4Q. And B has minus 3Q. And then I touch C and A together. Between the two of them, they have plus 1Q of charge, minus 3 plus 4, which means that after all is done, A is going to have a half Q on it. C is going to have a half Q on it, and B has minus 3Q. So now the problem asks us, what's the ratio of the electrostatic force between A and B at the end of experiment 2 to that at the end of experiment 1? So force between A and B at the end of number 2 relative to the force between A and B at the end of number 1. Well, we would use Coulomb's law to figure out the electrostatic force in each case. So in experiment 2, I would have the Coulomb constant K. The charge on A is a half Q, and I'm just dealing with magnitudes here. B is minus 3Q. I'm just going to write that in as 3Q, again, just a magnitude. And they are a distance d apart. So that's the force in experiment number 2. In experiment number 1, very similar, K. The ending charge on A is 2Q. B is also 2Q. And they are a distance d apart. And a whole lot of things cancel in this ratio. K cancels with K. D squared cancels with D squared. Q and Q cancel with Q and Q. And in the end, my ratio is 3 halves over 4, which you may prefer to write as 3/8. Second problem we looked at was this. In the figure at right, we have 4 point charges, and they're at the corners of a square. Q1 and Q2 are each 100 nanocoulombs, but this one is plus 100 nanocoulombs, where 2 is minus 100 nanocoulombs. 3 is plus 200 nanocoulombs, and 4 is minus 200 nanocoulombs. It asks me, what are the x and y components of the net electrostatic force on particle 3? Well, anytime I'm asked about net force, my inclination is to draw a free body diagram. So here's particle 3. Particle 3 feels a force from particle 1, and they're both positive, so it will be repulsive and down. And since this is the first force I'm drawing on my diagram, I can draw it any length I want to. So this is the force that 1 puts on 3. I'm going to go here next. 4 also puts a force on 3, but because they're opposite charges, they're attractive, so 4 would pull 3 to the right. And because the amount of charge on number 4 is twice as much charge as I had on number 1, but the distance away is the same, the force is then twice as big to the right, and we're going to take advantage of that when it comes to crunching the numbers to cut down on the amount of calculations that we need to do. So this is the force that 4 puts on 3. Finally, 2 and 3 are opposite in sign, so it's an attractive force towards charge number 2. And 2 has the same magnitude as 1, but it's further away, so that force up in the direction of charge 2 is the smallest of the 3 that we draw on the diagram. And so now when it's asking us for x and y components, well, the force that 1 puts on 3 is all in the y direction. The force 4 puts on 3 is all in the x direction. The force 2 puts on 3 is going to have an x component and a y component. But because of the geometry here, we know that this angle is a 45-degree angle. Okay. So let's use Coulomb's law and actually calculate how big these forces are. The force that 1 puts on 3, magnitude only, is K times the magnitude of charge 1 times the magnitude of charge 3 divided by A squared. That is 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Q1 is 100 nanocoulombs, so that's 100 times 10 to the minus 9 coulombs. Q3 is 200 nanocoulombs, 200 times 10 to the minus 9 coulombs. And the distance A is 5 centimeters, but I got meters here in my constant units, so I want to put my distances in here also in meters. So 5 centimeters is 0.05 meters. In order for the units to all cancel one another out. If you punch all of that in a calculator, you get this to be about 7.19 times 10 to the minus 2 newtons. Moving on, let's calculate the force that 4 puts on 3. Well, that's K times Q4 times Q3 over A squared, but I don't want to do any work here. The only difference is 4 is twice as big as 1, so my answer is going to be twice as big as what I had before. Put that in your calculator, and you get a force of about 1.44 times 10 to the negative 1 newtons. Here I'm keeping 3 sig figs per answer. Sometimes it's helpful to keep more until you get to your final answer so you don't have any rounding problems when you get the final answer. Last, we need the force that 2 puts on 3. So let's write that out. And that's K, let's see, Q2, Q3. And what's the distance? Well, this side of the square is A. This side of the square is A. So if you're a fan of the Pythagorean theorem, you know that this side, this distance right here, is the square root of 2a squared. The a can come out of here if you want. You can write that as the square root of 2 times a. But if I plug that in here, square root of 2 times a, and then I square it, I'm going to have k over 2 times q2, q3, a squared. Hey, this is all the same as up here. K is the same. The only difference is it's a half. This force is half as big as the force I calculated up here. So that is 3.6 times 10 to the negative 2 newtons. And now I have the 3 individual forces that make up this situation. I need the net electrostatic force in the x and in the y. So let's add up all the forces that are in the x direction. In order to do that, we're going to say, let's see, the force that 4 puts on 3 is in the x direction. So that's 1.44 times 10 to the negative 1 newtons. And then I need a x component of this force that 2 puts on 3. So that's going to be plus 3.60 times 10 to the negative 2 newtons times, and then because we're doing the x component here, the cosine of 45 degrees, or square root of 2 over 2, if you prefer it that way. And this works out to be about 1.47 times 10 to the negative 1 newtons. The similar sum is done in the y, but now the vertical component of the force 2 puts on 3 is up, the force 1 puts on 3 is down. They're in opposite directions. So I'm going to put that vertical component first, 3.6 times 10 to the negative 2 newtons times the sine of 45 degrees minus, since the other one is in the downward direction, 7.19 times 10 to the negative 2 newtons. And if I do the math on that, it comes out to about just over minus 4.5 times 10 to the minus 2 newtons. So there we have it. There is the x component of the force, the y component of the force, and that's where this problem asks us to get to. Some problems ask you to put those back together to find the magnitude of the overall resultant force, similar to problems that you did in Physics 1. The final problem of this problem-solving set reads as follows. In figure A, particle 1 of charge Q1 and particle 2 of charge Q2 are fixed in place on an x-axis. Particle 3 of charge Q3, which is 8 times 10 to the negative 19 coulombs, is to be placed on the line between particles 1 and 2 so that they produce a net electrostatic force on it. Figure B gives the x component of that force versus the coordinate x at which the particle is placed. The scale of the axis is set by 8 centimeters. And what are the sign of charge Q1 and the ratio of charge Q2 to Q1? Okay, so this right here is 8 centimeters, so we have to do a little deductive logic. That means right here is 6. That means here is 4. That means here is 2. And importantly, that means when we're at the 2 centimeter mark, the net electrostatic force on this third charge is 0. So I'm just going to blow up the x-axis for a minute here and talk about it so we can draw things a little bit bigger. So here is charge 2, and here is charge 1, and we don't know what the sign of those two charges are. But we do know that if we stick a charge in here at the 2 centimeter mark, it's going to feel a force in this direction, and it's going to feel a force in this direction. They're going to be equal to each other and cancel each other out. The problem is we don't know whether this force is coming from this charge and it's a positive repulsive force, or if this one's coming from over here and it's the attractive due to this being negative. There's no way of knowing just from the equilibrium position. It's the places to the left and right of 2 centimeters that you have to think about. For example, if I went to 3 centimeters, the graph is telling me that the force that the particle would feel would be negative. So if I inch this particle over here, what that's telling me is the force on this particle is negative, meaning the one that points back to the left is a bigger force than the one that points to the right. Or if we inch to the left from the 2 centimeter mark, so we get over here, now we have a net positive net force, which means the force component that's going to the right is larger than the one to the left. And both of those pieces of information tell us that this force over here must be the force that 2 is putting on 3, and this force must be the force that 1 is putting on 3. That means 1 is pushing a positive charge to the right, 2 is pushing a positive charge to the left. Since we know this is positive, we can deduce that charge 1 is positive and charge 3 is likewise positive. So we've answered the question about the sign of the charge Q1. How do we get the ratio of the charges? Well, let's focus on that equilibrium point where the forces are balanced. So at that point, we can say that the force that 1 puts on 3 is equal in magnitude to the force that 2 puts on 3. So let's use our Coulomb's law. K times the magnitude of charge Q1 times the magnitude of charge Q3 over the distance, well, that's 2 centimeters squared, equals K times the magnitude of charge Q2 times the magnitude of charge Q3 over the distance. And if this is 2 centimeters, this must be 6 centimeters. And again, a bunch of stuff cancels in these ratio problems. K goes away, Q3 goes away, and because I want the ratio of Q2 over Q1, I'm going to move Q1 over here and 6 centimeters over here. Let's rewrite that. Q2 over Q1. I'm dropping the absolute values since they're both positive charges anyway. Equals, let's see, 6 centimeters squared. Whoop, get the square in the wrong place. Squared over 2 centimeters squared. That's 36 centimeters squared over 4 centimeters squared. Centimeters squared cancels out, and I'm left with a ratio of 9 to 1, or it always troubled me to write a ratio as a single number, but you could write it as 9 as well and be correct here. So because Q2 is 3 times as far from the third charge as 1 is, you have to have 9 times as much charge at Q2 than you do at Q1. And note, the red herring in the problem statement, we never needed to worry about how big charge Q3 was, because as Q3 gets bigger, both of these forces would get correspondingly bigger and still produce a net force of 0 at this location.